All right, so let's get this started. Welcome back, week 2, cognitive psychology. And what we're going to be doing today is we're going to take a look at a special topic that really gives you a background in terms of, again, the approaches that we're going to be using and the ideas that we're going to be incorporating into our understanding of the human mind. But we're going to be doing it by revisiting the idea of representation that we had last week, and then also taking a look at artificial or alternative intelligence and how that has informed our approaches to cognitive psychology when we're trying to understand the human mind.
Yep. I had a question. So going through the Cengage stuff, are lectures more supplemental to the reading, or is the reading kind of independent from what we're going to be learning about in the lectures as well?
It's going to be both.
Okay.
So some of the lectures are going to be supplemental to the reading in terms of we're going to identify some of the more important concepts in the reading, and then we're going to take time in the lectures to go over those in more detail, maybe give you an alternative perspective on how to think about those. And then other ones are going to be added to the reading. So a lot of the stuff that we're doing on AI and representation, that is completely supplemental to what you'll find in the textbook. We are going to cover a little bit about my research, just so that we can have that sort of value added component to it. So it's going to be a mix of both. Starting off though, I do like to give this kind of basic principle, proof of concept kind of way of approaching cognitive psychology. But yeah, there will be literally the next lecture will be, hey, it's chapter 4. We're looking at attention. Let's pick apart some of the stuff that's in there.
Perfect. Thanks.
Mm-hmm. All right, so without further ado, we are back to talking about the human mind. So once again, and as today will make abundantly clear, the human mind is not the human brain. So I'm just going to keep hammering that in for a little bit, just until it becomes second nature to think of it in those terms. Because again, that was a thing that kind of shackled a lot of ideas about cognitive psychology for a while. But we are here thinking about the human mind. And as such, we're not doing neuropsychology. You're not going to see a lot of talk about neurons and localization of function, but we will be talking about how does your mind actually work. So again, we have this bias in our culture that the mind equals the brain. That is not the case at all. So we are going to remember as we move forward, the mind does not equal the brain. And what that means is that we then have to discover, well, what exactly is in the human mind and how exactly does that human mind work? So we're going to continue our look at how the human mind works by taking a look at how non-human minds work counterintuitively. But I think because you're going to see that the foundations of these two approaches share the same ideas. And spoiler alert, the ideas behind artificial intelligence and computer intelligence are what made cognitive psychology possible, and you'll see that in just a few moments. So what we're going to be doing today, we're going to have a quick recap on our information processing systems, on Mars tri-level hypothesis, and the idea of that representational level that we're trying to explain. We're going to take a look at the pandemonium model solution. So I posed you 2 challenges last class, and hopefully you worked through those to see how the pandemonium model, this really weird model that says we have demons in our mind that reside in different rooms, they get angry when they see certain features on a TV, how can that help us explain letter recognition? And then in addition, lead us to answer or ask questions that increase our understanding of how human minds work. And then we're going to turn it over to artificial or alternative intelligence. Why is it important to cognitive psychology? It's massively important because of the physical symbol system hypothesis. And we'll get to exactly what that is and why it opened the door for cognitive psychology. And then we're going to talk about Alan Turing's contributions, including the Turing machine. And we'll end with a look at the Turing test. All right, so an information processing system, just a quick recap. That's what we propose our human mind is. That is the approach that we use in cognitive psychology. So when you say that you're doing cognitive psychology, what you're really saying is, I think that the human mind is an information processing system. a system that takes in different pieces of information, such as orientation of lines, location of lines, and color, and then processes that into some new representation, and then can work on those representations and process them further with previous representations that are stored in memory. And then that leads us to our intellectual ability. That leads us to our behaviors and our thoughts. That basically leads to us doing what psychology is interested in understanding how we do. And we talked about Mars tri-level hypothesis. In order to fully understand an information processing system, that is, in order to fully understand the human mind, we have to understand it at 3 different levels. We have to explain how the human mind works at each of these 3 levels. The computational level, that is a problem faced. That is literally a list of the things that a human mind can do. So computational level will include things like recognizing letters, writing stories, recognizing faces, planning for your groceries on a trip to the grocery store. All of those things that we can do, those get listed in the computational level. So once we have a list of everything that the human mind can do, then we are done with the computational level and we're good. That part is finished. We then have the representational level. And these are the strategies that could be used, might be used in order to achieve what we can do in the computational level. So these are just sort of the strategies, the theories, the ideas about how information is combined in order to achieve what we do in the computational level. And then once we know strategies that can attest for everything that we do, that can explain everything that we're able to do, representational level is finished. And then finally, we have the implementation level. How is it actually done in a real physical entity? So how does our brain implement the part of the mind that it implements? How does our environment implement or create the part of the mind that it implements? Everything that is actually physical, that creates the mind, how is that actually done? And once we know that, then we have a complete understanding of the human mind, and cognitive psychology will be finished. Spoiler alert, it's not going to finish in the next, probably forever, but we'll get closer and closer every single year. All right, so we talk a lot about how we're going to stick in the representational level. That is going to be the place that we spend 99% of our time here in cognitive psychology. So what is a representation? Remember that this is a hypothetical internal cognitive symbol that stands in or represents external reality. It's a way of bringing external reality into the information processing system so that it can then manipulate that information. So it's a way of taking that external reality and putting it into information that can then go into the system. And the challenge for cognitive psychologists, or one of the biggest challenges for cognitive psychologists, is that that external reality can be represented in a lot of different internal representations. And part of our job as cognitive psychologists is to discover what are those internal representations. So you can take an external reality of two-ness, we have 2 of something, and you can represent it as the numeral 2, you can represent it as 2 dots, you can represent it in binary as 1, 0. There are a lot of ways that our mind could potentially represent that external reality of there are 2 of something. And an external reality can be very differently represented, and some of these representations makes things possible for our human cognition to do. Some of them make things hard for our human cognition to do. Some of them make things impossible for our human cognition. So you'll see it when we go to perception. There were actually some theories about our internal representations of perception. How do we perceive the real world that were rejected because they made perception impossible. They made it impossible specifically without the intervention of God. So basically scientists were saying, well, if it's impossible unless God allows you to perceive things, well, let's just not use that representation. So again, here we have that external reality of the United States of America. We have internal symbols of an imagery representation or a propositional representation. And an imagery representation makes it really easy to answer questions about east and west, north and south. A propositional representation makes it really easy to answer questions about distance, but distance is almost impossible to answer with, it's very difficult to answer with an imagery representation, and north and south and east and west is impossible to answer with this particular propositional representation. So we then finished off with a look at the pandemonium model. So again, this was a representational level explanation. This was a possible strategy that our mind uses in order to recognize letters. So what we're going to do now is we are going to take a look at the solution to the challenges that I posed as to whether or not it would be able to, or this solution here, as we have it listed here, would be able to recognize the letter P. So hopefully you work through this on your own, and you can check your solution against the solution we'll give right now. So off we go. So we see the letter P in the external reality. So it's an external reality, and then that gets represented in our mind on the image demon's belly. So that turns into the representation of the external world. That image gets sent to a TV, gets sent to a TV that is in a room filled with feature demons. And then those feature demons, again, start to disappear. This did not do this on my computer at home, but anyways, here we go. So those feature demons, if they see the feature that is on their belly, they get very agitated. In this case, I guess they get passive aggressive and they just leave. So that first feature demon gets very agitated and then sends a message to every cognitive demon that it's connected to. So it sees that up and down vertical line, gets very agitated and says, I got to tell everybody that I am really, really angry. There's a vertical line on the TV. So it sends its message to the F demon, sends its message to the P cognitive demon, it sends its message to the R cognitive demon. The next feature demon with the curve on its belly sees the same curve on that TV, gets very agitated, passively aggressively disappears, and says, I'm going to tell everybody on my contact list that I am really, really agitated. So it contacts the P demon and it contacts the R demon. And then that feature demon with the slash going from the top right to the bottom left doesn't see anything that makes it agitated. So it doesn't contact anyone. And then the feature demon with the slash going in the other direction doesn't see anything on the TV that matches its belly. So it doesn't get agitated either. So this is all the contact that we have for this particular letter P. So what then happens? Well, the cognitive demons start talking to each other, and the R cognitive demon says, hey, something must have been projected on the feature demon's TV screen, because I got calls from two of the feature demons. Two feature demons reached out to me to let me know how agitated they were. And now the P cognitive demon says, yeah, you know what? Something must have been going on in there, because I also got calls from two feature demons. And then the F demon said, well, you know what? I think something's going on, because I got a call, not that many. I only got a call from one feature demon. And then the Z cognitive demon doesn't even think that there was a situation, is completely unaware that anything was going on. At this point, the decision demon knows that something has been seen. However, now it's looking at the cognitive demons and it has a tie. It's got a tie between the R demon and it's got a tie between the P cognitive demon. And in this case, the model would propose that your decision demon would be confused. So this model, as it stands, cannot be the actual complete model of how we recognize letters, because we can distinguish between a P and an R. However, according to this model, we should be confused between what is a letter P and what is a letter R. So that would be the prediction. And in this case, what we would do is we would say, well, we don't have a complete model here. So we would either need to add more feature demons and more cognitive demons to this model, or abandon it in favor of some other model. So we either need to change this model or we need to come up with a completely new model, because as it stands, this representational level explanation would get confused between P and R. And in our computational level, we know that we can recognize P and we can recognize R. On the other hand, something like this, if it was very good at explaining other instances of letter recognition, and then it failed at P and R, it would probably be tweaked just a little bit, but then it would also start suggesting certain questions. Like, what are the letters that are most confused, you know, in letter recognition? And are there people who confuse these letters? So something like this type of a model might have something to say about individuals who are dyslexic and have difficulty distinguishing between lowercase d's and b's and p's and q's. Those are 4 of the letters that are very difficult for individuals with dyslexia. And this model might explain exactly why it is that that is occurring. All right, so that was the run through of would P be recognized in this model? As it stands right here, the answer is no. And then the second question that I posed was, what would this model predict would occur if an R was being viewed, but this time we had some brain damage so that one of the connections of the feature demons, specifically that slash from the top left to the bottom right, that feature demon lost its ability to contact the cognitive demons. So that connection there is severed. What happens in this case? Well, once again, we go through the process of the image demon projecting what is in the external reality onto the screen. The feature demons get very agitated if they see their feature, and they start contacting everybody that they have contacts with in the cognitive demons. So we have the first feature demon making his contacts. The second feature demon with the curve on its belly is making their contacts. That third feature demon doesn't see its feature represented, so it's not getting agitated. It doesn't contact anybody. And then that last feature demon with the slash that goes from the top left to the bottom right, it does see its feature and it does get agitated, but this time it doesn't have anybody to call, right? Its connection has been severed. It's lost its cell phone. It doesn't have the ability to contact a cognitive demon. So in this case, what occurs? Well, once again, we go to the cognitive demons, and that our cognitive demon says, well, something's going on in that room because 2 feature demons have contacted me. That P cognitive demon says something is going on in that room because 2 feature demons have contacted me. The F cognitive demon says, well, only 1 feature demon has contacted me. And that Z cognitive demon still had nobody contact him, still doesn't think that anything is going on. And now we see that there's 2 contacts to the R feature demon, cognitive demon, 2 contacts to the P cognitive demon. And once again, the model would predict that the decision demon would be unable to distinguish what letter is being perceived. So once again, letter recognition here would fail. There would be confusion between the R and the P. And once again, this, if it mimics what happens when people have certain types of brain damage, if it mimics what happens when, for example, there's brain damage due to prolonged alcoholism, this would be a potential explanation of what is going on in those cases. All right, any final questions about the pandemonium model and the solutions we just went through? All right, so let's get on to AI. So we're going to spend some time on artificial or alternative intelligence today. And the reason is because it's incredibly important to cognitive psychology. It's incredibly important to the foundation of what we're doing. And the reason it's important is because of the physical symbol system hypothesis. So before we get to the hypothesis, we need to understand what a physical symbol system actually is. And then that will help you connect the dots in terms of why this is so important to understanding the human mind. So what is a physical symbol system? Well, it's something that's physical that has symbols and is a system. Let's go through some examples. So a physical symbol system. One example of a physical symbol system is the abacus. So that is a thing that actually exists. It's in the real world. It's an abacus. And this is the first part of this is that a physical symbol system has to be a physically realizable system. It has to be something that actually exists. It has to be something that can actually be made or made of matter, exists in the real world. So let's get a cuter picture of that up there. So an abacus is a physically realizable system. It does exist in the world. So that is checkbox number 1 for a physical symbol system. Checkbox number 2, it has to contain a set of symbols. And what symbols are is they're basically physical patterns. All right, so this again has to be in the physical world. It's physical patterns that can be strung together in different ways. So we have physical patterns here that can be strung together. So we have the beads on this abacus. Those are physical symbols. They stand for things and they can be strung together. You can have 1 bead, 2 beads, 3 beads, all the way up to the 10 beads that are on a single line. Next criteria, it contains a set of processes that operate on the symbols. So there is a way to use an abacus. There is a way to add, to multiply, to divide, to subtract when you're using an abacus. I don't know how to actually use an abacus, but if you've ever seen somebody that does know how to use an abacus, like this pharmacist in China, it is pretty magical if she's going to move. Can we get it? That is somebody who actually knows how to use an abacus using an abacus. And they are doing calculations at a pharmacy. All right, so there we have, clearly there are a set of symbols, clearly there are processes that operate on those symbols. Clearly the processes that need to operate on the symbols that play the video are not there right now, but anyways, there are processes that operate on the symbols. That's the next requirement for a physical symbol system. And then the last requirement for a physical symbol system, and that it's got to be located in the wider world. So it's got to be located in the real world of real objects, and it needs to be related to that world by what's known as designation and interpretation. So designation means that things in the external world can be represented in this physical symbol system. All right, so things in the external world, such as the number 4 or the idea of 4, can be designated in this abacus, this physical symbol system. So 4 beads on the abacus means the number 4 in the real world, and 2 beads slided to the left in or slided to the right on that second bar, that means 20 in the real world. So the real world idea of 24 can be designated, can be placed into, can be represented by this physical symbol system of the abacus by moving those beads over to the other side. So that's a relation by designation. Information can go into the system. The last thing we need is relation by interpretation. And what interpretation means is that information can then go out of the system as well. So another cognitive entity can take a look at this physical symbol system and say, oh, okay, I can interpret the symbols there because I know that those 4 beads mean 4, and I know that those 2 beads mean 20. So I can interpret that physical symbol system and understand that it means 24. So that's a first example of a physical symbol system. Pretty simple example, the abacus. We can get a little bit more complicated. So we have other physical symbol systems that are physically realizable. And one of the ones that we use very often in our society is the computer. So the computer is a physical symbol system. It is a physically realizable system. They do exist. We've got one right here. It contains a set of symbols, physical patterns that can be strung together. In this case, the symbols are 1s and 0s, and these are little microprocessor switches that switch from on and off. That is literally what your entire computer is based on. They're looking for new physical patterns now with quantum computing, but up until now, it's just been binary on and off switches. But again, these are physical patterns. And you can put these physical patterns together. You can put a whole bunch of ones and zeros in a row, and they can be strung together. So criteria number 2, check. Criteria number 3 contains a set of processes that operate on the symbols. Computers do. They contain programs that have specific rules about what you do when you encounter a 0, 1, 0, 1, 1, 0, 1, 0, 1, right? It says what you do when you encounter these internal symbols, how to operate on them, how to change them, how to modify them. So it contains those set of processes. So criteria number 3, I believe. And then it's located in a wider world of real objects, once again, by both designation and interpretation. So designation, if you go to the Wikipedia article on physical symbol systems, somebody, specifically the writer, was able to put into this physically existing thing, it was able to put in the representation of what a physical symbol system is, right? So that is designation. And then somebody else, specifically the reader, can come by and can interpret that, right? So the idea of a physical symbol system can be represented, designated in the physical symbol system of the computer. And then that designation can be interpreted by somebody who's reading that output. And that's how it's related to that wider world. All right, so that's 2 examples of a physical symbol system. Any questions on physical symbol systems before we bring up the idea of why we have these? All right, so why did we spend that time understanding the physical symbol system? Well, it has to do with these 2 researchers, philosophers, theorists, computer scientists, Alan Newell and Herbert Simon. Don't ask me which one is which, but Newell and Simon, they proposed the physical symbol system hypothesis. And what that hypothesis says is that a physical symbol system has the necessary and sufficient means for general intelligent action. So general intelligent action is the idea of a physical symbol system can do general cognition. It can do general cognitive things. It can do general problem solving. It can do general computation. It can basically, a physical symbol system is not restricted to just adding numbers together, right? It's not restricted to just navigating a map. A physical symbol system can do general intelligent action. And it is sufficient to do that, which means that in order to do general intelligent action, you only need a physical symbol system. You don't need more than that. You don't need to add to it. If you have a physical symbol system, then that is enough for general intelligent, or a physical symbol system is enough for general intelligent action. And then the necessary part of it is indicating that it is what is required. So the necessary means that what is required, what is needed. A physical symbol system is the required part that we need for general intelligent action. Now, this one is a maybe, because as we are kind of trying to discover now, there might be other ways to do this. We can't really think of other ways to do it. Our minds might not be capable of thinking of other ways to do it. But whether or not it's necessary is a big maybe. But whether or not it's sufficient, that is another thing, because what we're looking to do is we're looking for an explanation of general intelligent action. So if a physical symbol system is actually sufficient, if it is enough in order to get general intelligent action, then if you have this physical symbol system, then you have the ability to do general intelligent action. So that is extremely important for cognitive psychology, because one of the physical symbols that we encounter every single day, and we actually cannot not encounter it, are humans. Oh, the video works. Sweet. All right, so here we have this human here. And as you might imagine, humans are physical symbol systems. So a human checks off all the criteria for a physical symbol system. So we are a physically realizable system, right? We're here, we're made of stuff, we actually exist. So check off that first box. We contain a set of symbols, physical patterns that can be strung together. In this case, this is one of the few times we're going to talk about implementation. So we actually do have these physical symbols, and they're called neurons. And neurons have connections. So a neuron can either be firing or not firing, and it has connections to other neurons, and it has rules for those connections. It either makes them more likely to fire or makes them less likely to fire. But these are actual physical things that can be strung together, and your brain is that entire stringiness of it together. I would also argue that there's physical patterns in the environment that can be strung together as well to augment or to contribute to what your human mind actually is. There's physical patterns in your cell phone that can help you with cognition, but we're going to keep it simple right now. Physical patterns that can be strung together. At the very least, we got neurons in our brain that can be connected to other neurons, can be strung together. We have a set of processes that operate on these symbols. So we have a set of processes that operate on neurons and how they fire and whether a connection is excitatory. So if one neuron fires, it makes the next neuron more likely to fire. Is the connection inhibitory? When one neuron fires, it makes the next neuron less likely to fire. There are rules about how these are interconnected. You have neurons that are connected to specific other neurons and not connected to alternative neurons, right? So we have neurons in the visual cortex that are not connected to neurons in your auditory cortex. So we have these different rules and processes that operate on these symbols. And then finally, we have the idea that this physical symbol system is located in that wider world of objects, and it's related by designation and interpretation. So the designation portion of this would be when this individual learned how to breakdance. So breakdancing is a thing. Breakdancing is a physical activity that exists in the real world. And the designation portion that is required to link this individual to the real world was him learning how to breakdance. And then the interpretation part of it is if we look at this and we recognize this as breakdancing, then we are interpreting those internal representations correctly. So designation would be the learning portion, and then interpretation on our end would be the recognition that that is actually what is taking place. So human beings are physical symbol systems. And because of that, according to the physical symbol system hypothesis, we have the necessary, meaning that we are the only ways to do it. This physical symbol system is the only way to do this. That one is more questionable these days. But importantly, we have sufficient means for general intelligent action, which means that we have enough in order to do general intelligent action. And whether or not this hypothesis is true is something that we're going to turn to in just a moment. But very, very importantly, if this hypothesis is true, then we have a way, we have a procedure, we have a model in order to understand how do we do general intelligent action. And what this means is that if we want to understand our super complicated mind, and we want to understand how does our mind operate, how does it process information? Well, to look at something that's super complicated is very difficult. And maybe we need a model. But what's the right kind of model? What should we look at? How should we approach human cognition? And this hypothesis, if it's true, says that if you want to understand human cognition, you basically want to understand a physical symbol system, because that's what our minds are. They're a physical symbol system. So if you want to understand a physical symbol system that's super complicated like the human mind, maybe a good place to start is to start with a simpler model, like an abacus. And let's see if we can understand how an abacus works and develop theories about how abacuses actually operate. And then as we get more understanding, we can move to more complex and complicated models. And you can actually see this working through in the history of humanity, because human beings at one point had no idea how the human mind worked. Descartes thought that animals, you could possibly understand animal cognition because animals were all reflex, but you had no chance whatsoever to understand the human mind. The human mind could not be understood. And then throughout the history of mankind, we just kept intuitively saying, well, you know what, how about these physical symbol systems that are operating? Maybe that's what the mind is like. So we would say, well, maybe the mind is like a clock, right? That's the most complicated thing we have right now is a clock. Maybe minds work like clocks. And then when computers came along, we were like, well, maybe minds work like computers. What we were saying is that we were recognizing that idea that we're a physical symbol system. So a way to understand human cognition is to understand how physical symbol systems work. Because if we are a physical symbol system, which we are, there's no questioning whether we're a physical symbol system, but if that is enough for general intelligent action, then that is our opening into the world of trying to understand human cognition. So is this hypothesis true? Is a physical symbol system sufficient? Is it enough for general intelligent action? Because if it's not enough, then we need to look elsewhere to understand human cognition. We need to look elsewhere to understand the human mind. Well, is it enough? To answer that, whether the hypothesis is true or not, we're going to turn to Alan Turing. Now, Alan Turing was an English mathematician, computer science, a logician, cryptanalyst, philosopher, theoretical AI biologist. He was one of the greatest minds, I think, that probably ever walked this earth. If you want a really compelling overview of his contribution, especially to the war effort and cracking the Enigma code, there's an excellent film called The Imitation Game where Benedict Cumberbatch plays Alan Turing, and you can see him here with his physical symbol system that he made that basically allowed Britain to crack the secret code that the Germans were using in order to send orders out into the field. And very, very compelling, very cool film. But importantly, illustrates the idea of what Turing called a Turing machine. So he was a genius. And you know what? Name it after yourself. I think he deserves it. So a Turing machine. What is a Turing machine? Well, a Turing machine, it's a mechanism with a finite number of programmed states. So that's very important. It's a finite number, right? So we're not talking about something infinite. It's something that has a certain number of programmable states. And this thing takes in inputs and it gives outputs out as symbols. And these inputs and outputs, these symbols, they are a finite alphabet. So once again, we don't have to make up an infinite string of symbols. We can make a Turing machine with just a finite set of symbols. So people have actually built Turing machines. This is an example of a Turing machine. And technically, the only thing that is inaccurate about this Turing machine is that the amount of tape that goes through the machine would need to be infinite, or at least near infinite. So basically what that means is that you would have to have a constant amount of tape that could be supplied to the system. So much like if you wanted to use a printer over and over and over again, you need to have that constant flow of paper going into the printer. You need that constant flow of tape going into a Turing machine. So that is a Turing machine. It's a very, very simple, it's not a simple mechanism, but it's a realizable mechanism. It's something that is doable in the real world. So what does a Turing machine actually do? So let's get away from this image and we'll go to a schematic of a Turing machine. All right, so a Turing machine, what it can do. You see here the components of a Turing machine. We have there on the bottom left and the bottom right, we have the tape mover. So this is what actually moves the tape along physically. We have, you can see at the bottom, logical control. eraser and writer, scanner. We have the memory dial. The memory dial is what maintains the states of that the machine is in. And you can see there's only 6 states, right? The memory dial points to 1, 2, 3, 4, or 5, or 6. Those are the 6 states that the machine can be in. So what does a Turing machine do? Well, first it scans. It takes the symbols as inputs one at a time. So you have a scanner that can read what is on that tape. So it is a vertical line. Is it empty? Is there an X there? That's what the scanner can do. So it scans inputs one at a time. And then it has operations. So the eraser and writer, the eraser can either erase the symbol or not. So whether it erases the symbol or whether it does not depends on the state that the machine is in. So it can either erase the symbol or not. It can either print a new symbol or not, right? And that is done using the writer. And then either of those actions can then change the state of the machine or not. So it can basically see that there's a slash and say, all right, I see a slash and we're in state number 1. When I see a slash and we're in state number 1, I'm going to erase that slash. I'm going to write an X where the slash used to be, and I'm going to change that memory dial from a 1 to a 4. And that's basically what a Turing symbol does. And once it does that, it moves on to the next symbol with the tape mover. The tape mover basically just goes to the next symbol in the machine. All right. So everybody clear on what a Turing machine can and cannot do? Very, very simple, very straightforward. Does very few things. Again, reads a symbol, erases it or not, writes a new one or not, changes its state or not, moves on to the next symbol. That's all it does. So why are we talking about Turing machines? Well, we're talking about them because of what they can actually do. So before we get there, just to kind of drive the point home, they're a physical symbol system. They're a physically realizable system. They actually exist. You can actually make them. They contain a set of symbols, physical patterns that can be strung together. So they have that finite alphabet. So we don't have to continually supply them with new alphabets in order to do new things. They have a finite set of alphabets. They contain a set of processes that operate on those symbols on that alphabet. So they can erase or not, write or not, replace or not, and then go on to the next one or change the memory dial. So they contain that set of processes. And they're located in the wider world of real objects by designation and interpretation. So somebody can program this by writing symbols on the tape. That is the designation portion of it. And then somebody can interpret what the Turing machine outputs by taking a look at the tape and saying, oh, okay, vertical slash X space XX vertical slash space. Oh, okay, that's the number 7, for example. So that's the designation and that's the interpretation. It's located in that wider world of objects by being able to take the external reality and designate it, represent it in the tape. And then somebody who knows how to read the tape when it's after it's been processed can then interpret that tape and bring the output back into the external world. So a Turing machine is a physical symbol system. So what? So why are we talking about a computer that was, spoiled myself. Why are we talking about a machine that was invented in the 40s or the 50s? Well, the reason is that unlike the physical symbol system hypothesis, where Newell and Simon basically said, we hypothesize or we propose that this is the case, Alan Turing proved logically, without a shadow of a doubt, showed in a proof that given enough time and enough tape, that simple Turing machine can perform any computational task. So that little Turing machine, that thing that I just showed you that has that finite set of symbols that can read the symbol, erase it or not, write a new one or not, change the state or not, move on to the next symbol, that can perform any computational task. That thing can add numbers together. That thing can divide numbers. I'm kind of stuck on math now. That thing can do calculus. That thing can make you or represent an image, right, as a JPEG. That thing can basically do any cognitive task. This thing can basically do any cognitive task. And again, this is not something that Turing was like, well, I kind of think this might work. This is something that he actually proved as a proof that if you give this thing enough time and enough tape. Now, something like that might take you 14 years to divide two numbers, right? So it's not practical, but the important thing is that it's possible. And when I think about what this means and the contributions that he made and the idea of this, I really hope this clip works. It just kind of blows my mind. And when you think about people who have existed on this earth that actually might be superheroes, Alan Turing is one of the ones that comes to mind. And when I read this, I immediately thought of this scene from Iron Man.
It's impossible.
All right, so something like this boggles my mind today. And I just keep thinking that Alan Turing did this in the 50s in a cave, with paper, and was able to prove all this. I mean, it just kind of boggles my mind that somebody like this could have just have existed, on this world. If you're more interested in Alan Turing, I would highly recommend Imitation Game is great. One of the biggest tragedies of Alan Turing was that he was a homosexual when it was illegal, and his ending is not good. And you just kind of like think of what could have happened to humanity if Britain got behind this guy. If they said, look, you know what? You are an amazing mind. We are going to put resources behind you. We're going to put funding behind you. We're going to give you access to the things that you need to do the wonderful things that you do. Where would we be today if he wasn't cast aside because he was illegal at the time? Like not ostracized, not socially outcast, literally against the law. It just boggles the mind. I think we would literally be probably in like wherever we're going to be in 21, 25. If Britain backed this guy, we'd be there today. All right, so back. All right, so AI Turing machines. So can do any cognitive task. In other words, a Turing machine manipulates symbols. So if we define cognition in terms of manipulating those symbols, if we decide as psychologists, we're going to define what we do in our human mind as manipulating symbols, well, then this is a proven, again, he proved this, viable strategy for cognitive psychology. Cognitive psychology has the potential to explain any cognitive task using a physical symbol system that manipulates symbols. And this is something that Alan Turing has proven. So we are not wasting our time here. We have a proven viable strategy that we can use in order to understand our minds. And that is what cognitive psychology was built on. The idea that, okay, we got these symbols, we manipulate these symbols, and that's what cognition is. And that's not just a feeling, that's not just a hope, that's something that is true because Alan Turing proved it. All right, so the last thing we're going to talk about is the Turing test. And this comes by, again, Turing was like really future forward thinking. And he showed that any cognitive task, any task can be implemented in a Turing machine. So the idea then for him was, well, how much implementation do you need? How many things do you need to implement in order for mentality to be reached, in order for a thinking machine to be made? So I'll give you a kind of scenario for this. Let's say that you get hired on at some large tech company who is working on AI. And they say, all right, we're going to give you all the resources that you need. we want you to go ahead and build a machine that can think. We want you to build something that has general intelligence. And you tell them, you go, all right, no problem, I'm gonna do it. So you go away, you come back in a week, and you tell them, you know what, I did it, I have a machine that can think. And they're like, great, what does it do? And you go, it adds numbers together. And they're gonna tell you, go back, it's not enough. So you go back and you work on it a little bit more. And then you come back and you say, you know what, I've done it, I've got a mind. I've made this thinking machine. And they go, what can it do? And you say, it can add numbers and it can read sentences. And they tell you, go back. And you can play this game back and forth, where you keep implementing, you keep adding stuff, adding abilities, adding cognitive tasks that your machine can do. And the question is, when do you walk into that room and say, all right, I've made this machine, it can add numbers together, it can understand, it can read sentences, it can do this, 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 it can do this. 2 hours later, you're like, it can do this, and it can do this. And the person that you're working for says, you know what, you did it. It's done. We have a human mind. When does that get reached? When do we get mentality? Or what is, in other words, what is a sufficient condition for mentality? When do we know that we have made something with enough cognition in it that it now has a mind? Or we can say that it is now a thinking entity. And Turing came up with his criteria for this. And much like the Turing machine, he called this the Turing test. All right. So this is the last thing we're going to end up on the Turing test here. So the Turing test, it's based on a couple of ideas that might seem a little, well, one of them might seem a little counterintuitive. But when you think about it for a moment or two, you'll see that it makes sense. So it's based on the ideas that we know that we have minds. And we know that we have minds because of introspection. So basically, if you want to know whether or not you have a mind, you can just kind of introspect and take a look at your thoughts and say, you know what? Do I have a mind? Yeah, you know, I guess I do. I guess I do have a mind. And this is one of those things that we just kind of take as almost a base, a priori type of realization, right? So in philosophy, you got Descartes going, you know what, I think, therefore I am, right? I have a mind, therefore I exist, right? So we know that we have minds, and we know that through introspection. So we're conscious of the fact that we exist, that we think, we know that we have these minds. We don't know at all, as you'll discover during this semester, we barely know how they work. So introspection is a horrible tool for discovering how your cognition actually works, but it's a great tool for knowing that you do have cognition, right? Because again, we can just introspect and say, yeah, you know what? I'm pretty sure I have a mind. But we can't do this with other people. We cannot introspect into other people's minds. There's no such thing as extrospection, right? It's introspection. So we know that we have minds, but we only believe that other people have minds. So I'm a firm believer that everybody in this room has a mind. I am only certain of that for myself, but I believe it's true of other people, and I interact with other people as if I believe that they have minds. But you need to understand, for the Turing test to make sense, that there's no basis for this assumption. There's no absolute basis. I'm going to say this another way. There's no absolute basis for this assumption. There's no proof of it. There's no way that I can actually see your mind or experience your mind directly in order for me to say, yes, your mind actually exists. So we come up with the idea or the belief that other people have minds. And what Turing asked is, well, what is the best evidence for minds, right? When do we say, oh yes, this person here has a mind? And according to Turing, the best evidence was, yeah, it should be a video. Well, all right. The best evidence is conversation, right? The conversations that we have with people is our basis, is our best evidence that we gain in order to understand that this person has a mind. So to put that in another way and hopefully convince you a little bit more, let's take it into the realm of science fiction. Let's say that we meet a non-human. How would we determine if that non-human has a mind? So let's say that we're a veterinarian and we're going off on a call to a farm, and we just have a nice farm side manner, I guess, with our patients. So we're talking to this cow and we go, "Hello there, Mr. Cow. I just realized this is the worst veterinarian ever. Hello there, Mr. Cow." And the cow goes, "Moo." Would you say that that cow has a human-like mind? If that was the response. I will take by your silence that you mean no. So nobody in their right mind would go running to the newspapers and saying, "Oh my gosh, I found a cow and it has a mind. It's got a human-like mind." Why? Because when I said, "Hello there, Mr. Cow," the cow said moo. That is not enough. We would in no way say that that cow has mentality, that cow has a human-like mind. However, let's say that we went there and we say, "Hello, Mr. Cow." And the cow says, "Hello, Mr. Scientist." At that point, we'd be like, "Oh my gosh. Now there's evidence, right? Now we got a little something going on here. Maybe this thing has a human-like mind." So we go, "Hello there, Mr. Cow. I didn't know cows could speak." And the cow says, "Hi, Mr. Scientist." And you say, "Can you say anything else?" And the cow says, "Hi, Mr. Scientist." Well, in this case, we have a very cool kind of parlor trick, kind of cool circus trick, right? We have this cow that has an ability that is very unique, that is very much unlike anything we've ever seen. However, the conversation just doesn't pass the sort of criteria that we need in order to say that this entity, this thing, this cow has a mind. So once again, even though the cow can speak, even though the cow can say, "Hi, Mr. Scientist," we would again conclude, you know what, you don't have a mind like I do. You don't have a human-like mind. However, if we went there and we said, "Hello there, Mr. Cow," and the cow said, "Hi, Mr. Scientist," and you say, "I didn't know cows could speak," and they say, "Well, I'm a cow and I can speak," and you go, "This is utterly fantastic," and the cow says, "We can't be friends." At this point, you would say, you know what? There's something here. There's some intelligence here. There's some human intelligence here. Yes, there is mentality. Yes, there is a human-like mind in this cow. So it's not in a physical form that we're normally would see. But I think if anybody encountered a cow that was like this, they would be super surprised, super excited, calling the paper saying, "You know what? I found a cow and this cow can think. This cow is intelligent. This cow has a mind." So that's the basis of the Turing test. So the Turing test is the idea that we use conversations in order to determine whether something has a human-like mind. Yep.
This is only applicable to conversations, because we can teach animals how to do tricks and where they would need to go to eat or to feed, which would indicate that there is some mentality there.
Good point. So this is limited only to conversations.
Okay.
But we are going to get to your point because that is actually a really, really important thing to remember with the Turing test. So we don't want the Turing test to be used incorrectly. And if you were to say that because you don't pass the Turing test, you don't have a mind, that's incorrect. But as we're going to see, we're making the argument that if you do pass the Turing test, then for sure you have a mind. And that's the idea. All right. So, but awesome, really, really good point. So the Turing test, it's framed as an imitation game. So this is the actual way that you would do a Turing test if you were going to do it according to how Alan Turing laid it out. So you got two rooms, and in one room, and we'll go the AI route for this, in one room you have a computer. And this computer is running some sort of artificial intelligence program. And in another room, you have a person, and that person is communicating via basically like a text program. So Alan Turing did this in the at the time that he was doing it because he didn't want the Turing test to be failed just because a robot's voice sounded weird, and he knew that voices would be something that, or he I guess, theorized that voices would be something that would be incredibly difficult to make human sounding. And it has been, it has been a long time since robots and artificial intelligence, since machines could produce sounds before it actually got to anything that sounded like a human. So the Turing test is framed as an imitation game. You have two physical symbol systems, one in room A, one in room B, and they're communicating via text. And they're communicating to a third person, and that person is the judge. And the challenge is that person needs to determine which of these rooms has the human and which of these rooms has the computer. So what does the human do? Well, the judge basically asks some questions. And it might start off with, well, what is the capital of France? And room A will send them back a response and say it's Paris. Room B will send them back a response and say Paris. So in this case, no information, right? No way to distinguish between the two minds in those two rooms, or potential minds in those two rooms. All right, next it might ask, the judge might ask, which of the following would you most prefer? Would you prefer a puppy, B, a pretty flower from your sweetie, or C, a large properly formatted data file? And room A might say C, and room B might say B. And then at this point, you might say, okay, I know which one is the computer. Room A is the computer, room B is the human. And in that case, the computer failed the Turing test. So the idea is that if after a series of questions, the human judge, the human person that is asking these questions cannot tell which room has the computer and which one has the human, then that computer has demonstrated mentality. That computer has a human-like mind. That computer has general intelligence. So if the questioner identifies a room with a human in it at chance levels, then that computer has a mind. And this is really the same as giving other people, the benefit of the doubt. Because the only way that I know that anybody that I encounter has a mind is because they can basically converse with me or behave with me or interact with me in a way that indicates that they have a human mind, in a way that indicates that they interact the same way that other people that I assume have a mind would interact. And I am not able to tell the difference between them and different people before. Basically, I said that horribly, it's the benefit of the doubt that we give other people. We're now applying it to computers. So this is, yep.
Is that not just testing its ability to mimic instead of if it has a mind?
That is also a very, very good question. And that is something that we are going to dive into a little bit more next class. But the idea is that, does it indicate that this thing actually has a mind, or is it just mimicking a mind? And I would argue, I'm on the side of, I would argue that we should conclude that it has a mind and not that it's mimicking a mind. Because when I'm conversing with you right now, I am not thinking at all that you are just mimicking, right? But why not? You have not used any new words, right? You have used words that I've heard before, and you have put them in the structure of a sentence, and specifically a question. And I have heard that structure before. And you know, it might be a unique sentence that was never uttered in the history of humanity, but it is made up of pieces that have been before. And yet I would not at all say, well, you're mimicking. I would say, well, here's a rather intelligent question from a human mind. So the question is, and we'll touch on this next time, is should we only reserve that benefit of the doubt to other biologically human things? Or do we take the criteria that we use with humans, and do we apply them to other things? And we're going to see that humanity has a very, we're going to talk about moving the goalposts next class, which is a kind of logical fallacy that is oftentimes used in arguments. But humanity has this deep-seated idea that we are the absolute pinnacle of cognitive ability in the universe, right? We are the top, and we take great pride in being the top. And if you take a look at a lot of religions, such as Christianity, it's put in there that we are the pinnacle of creation. We are the absolute top. And one of my favorite studies, and I can't find it, and I wish I could, I encountered it when I was an undergrad, was about how do you define intelligence across species, right? So what is a marker of intelligence across species? And people thought to themselves, well, you know what? It's brain size, right? Whoever's got the biggest brain is going to be the most intelligent species. And then biologists were like, so you mean dolphins, right? Dolphins are smarter than humans. And they were like, no, well, that can't be it, right? That's not the way that you measure intelligence. It can't be brain size. It's got to be brain size to body weight ratio, right? It's the size of your brain to the size of your body. That's the true measure of intelligence, because we beat dolphins on that measure, but we lose to birds horribly on that measure. So all of a sudden, all the bird people came by and they said, oh, so birds are the most intelligent. And everybody was like, no, that can't be it. And they came up with this convoluted equation where finally humans came out on top. And they were like, yes, that's gotta be the one that explains human intelligence. We will do almost anything to remain on top of the cognitive pinnacle. And it reminds me of just this one example or one idea. And this is from Neil deGrasse Tyson, although it's not his idea. A lot of people are asking, is there intelligent life in the universe? And one of the big questions is, if there is, why hasn't it visited Earth? Why haven't intelligent species from outer space actually ever come to Earth? And Neil deGrasse Tyson made the point that there is a huge amount of hubris in that statement to think that we are smart enough or important enough or advanced enough for any other civilization to take an interest in us. And the reason that we haven't been visited by other aliens might be the same reason that you don't go visit an anthill. Because as far as we are advanced in cognition compared to ants, it could be that other alien species are that much further advanced than us, and we are just not interested in them. But it's hard to imagine that, because again, we look at our own minds, we introspect and we say, you know what, this is pretty fabulous. Who wouldn't want to know this? The truth is, maybe the rest of the universe.
So is the Turing test testing if it has a mind or if it has a human-like mind?
As is mentioned here, it'd be human-like mind.
Okay.
Which is to say that it does have a mind. But importantly, and we'll see this just right now, it vastly overshoots it. So what the Turing test is, it's a sufficient condition for mentality. So the argument is that if you pass the Turing test, humans pass the Turing test. So if a machine passes the Turing test, then it also has a mind like humans, right? The question though, whether it's necessary, is very different and probably false. Because really what we're asking here is that, is there anything that we believe has a mind that wouldn't pass the Turing test? So if the Turing test is sufficient for saying that something has a mind, then basically what we're saying is that you pass the Turing test, we're going to say that you have a mind. But is it necessary? If it's necessary, then we're going to say that if you fail the Turing test, you don't have a mind. And that people don't believe, because we can think of a lot of things that have minds that would not pass the Turing test. So a few things, I think dogs have minds, but a dog would horribly fail the Turing test. It would not take you more than one question to realize that the thing in room A is a dog, or not a dog, but definitely not a human mind. Now, dogs would not pass the Turing test. I would argue that dogs do have minds. Let's take it a little bit further. Babies, human babies, would fail the Turing test, right? Human babies can't do, they don't know what the capital of France is. They don't even know what A, B, and C is, right? And yet we probably do not want or wouldn't say that a human baby does not have a mind. And then what about people with certain intellectual disabilities? What about somebody that is severely autistic? So my son is on the autism spectrum, and we do not have typical conversations with him. There's a lot of scripting, there's a lot of repetitiveness. Basically, what I'm saying is that if you put my son in room A and you put a neurotypical individual in room B, it would not take you very long to know which one, it would not take you too long to distinguish between the two. And my son would fail the Turing test. Does that mean that my son doesn't have a mind? Well, I would say absolutely not, because in interactions with him, you can definitely see there is cognition there is awareness, there are the things that make up the mind. So the Turing test, to just kind of cap it off here, it's not a necessary condition for a human mind, right? Or a human-like mind. It's not a necessary condition for mentality, right? Let's take it a little bit broader. It's not a necessary condition for mentality because dogs fail the Turing test, but dogs have minds. Babies fail the Turing test, but babies have minds. People with intellectual disabilities fail the Turing test, but they have minds. But what it is, and what I would strongly argue for, is that it's sufficient. So that if you have something that passes the Turing test, then it is inconsistent with how we interact with each other to say that that thing that passed the Turing test does not have a mind. And as we're going to see next time, that idea has come under a lot of fire recently, because for the first time in human history, we have something that can pass the Turing test. And it's these large language models. ChatGPT can pass the Turing test. So now the question is, do we want to admit that ChatGPT has a mind, or do we want to say, no, that's actually not a mind? And we're going to talk about that and the idea of moving the goalposts next time. But that is all that we have for today. So next time we're going to take a look at moving the goalpost. We're going to take a look at a little bit more about the Turing test and some of the implications, but we're also going to start up on attention. So take a look at chapter 4 to get ready for that class. But other than that, we are done for the day.